Ever wonder where all the light in the universe comes from? Let's journey back to the birth of the cosmos, a time shrouded in mystery, the cosmic dawn. In the early moments of the universe, space was not as we know it today. It was a hot, seething cauldron, churning with a dense fog of ionized plasma. This was a time before stars, planets, and galaxies. Everything was unformed, a formless mass of energy without shape or structure. This early universe was also cloaked in darkness. Not because there was no light, but because the light that existed couldn't escape the dense fog. Photons, the particles that make up light, were trapped, bouncing off the free electrons floating around in the plasma. The universe was dark, not due to an absence of light but due to the light's inability to shine through the fog. As the universe aged, it began to cool. After around 300,000 years, an important transformation occurred. The universe, once a hot, chaotic soup of ionized plasma, began to change. Protons and electrons started to come together, forming neutral hydrogen and traces of helium gas. Why is this significant? Well, neutral gases have a unique property. They allow most wavelengths of light to pass through them. This meant that light, once trapped, was now free to move. But there was one problem. There were very few sources of light in the universe at this time. This transformation from a dense fog to neutral gases set the stage for the birth of the first stars. These stars, born from the hydrogen and helium, would eventually light up the universe, giving us the cosmos we know today. This was the cosmic dawn, a time of change, a time of beginnings. It was a critical period that laid the groundwork for the universe's evolution, setting the stage for the symphony of stars, galaxies, and cosmic wonders that we see today. Out of the darkness, the first stars were born. Imagine a time shortly after the Big Bang, when the universe was nothing more than a hot, dense fog of ionized plasma. Light was a scarce commodity, with photons scattering off freely floating electrons, rendering the universe a black void. But as the universe cooled, something remarkable happened. After about 300,000 years, protons and electrons began to join forces, forming neutral hydrogen and a smattering of helium gas. This neutral medium was permeable to most wavelengths of light. However, there was a catch. There were very few light sources to produce this light. Enter the first stars. These cosmic entities originated from the very hydrogen and helium that filled the early universe. These weren't just any stars. They were the universe's pioneers, the first to break the cosmic darkness. The radiation they emitted was powerful, so powerful that it could strip electrons from their nuclei, reionizing the gas that filled the universe. Now you might be wondering, what's the big deal about reionization? Well, reionization allowed light to shine out into the universe. Before this, the universe was so dense that light couldn't penetrate it. But with the birth of these first stars, the universe had expanded, and the gas had become diffuse. Light could finally break free and illuminate the cosmos. By about 1 billion years after the Big Bang, the universe was entirely reionized. The end of the cosmic dawn had arrived and the universe was no longer a dark void. It was now filled with light, thanks to these first stars. The birth of these first stars marked the beginning of a brighter universe. They were the cosmic torchbearers, lighting the way for future generations of stars and galaxies. They turned on the lights at the dawn of time, setting the stage for the complex and beautiful universe we know today. The birth of these first stars wasn't just a cosmic event. It was a pivotal moment in the history of the universe, the first spark in the darkness, the genesis of all that was to come. As the universe expanded, the gas became diffuse, allowing light to shine out. This is where our journey into the reionization of the universe begins. Imagine the universe 1 billion years after the Big Bang. It's a time of transformation, the end of an era known as the cosmic dawn. But to understand this crucial period, we first need to delve into the process of reionization. So, what is reionization? In essence, it's the process that brought light to the dark and formless void of the early universe. It's a cosmic makeover, where the universe transitioned from a thick, murky fog of neutral hydrogen to a clear, illuminated expanse. Following the Big Bang, the universe was a hot, dense fog of ionized plasma. Light couldn't penetrate this fog, and photons were scattered off free electrons, rendering the universe dark. But as the universe cooled, protons and electrons began to form neutral hydrogen gas, which most wavelengths of light could penetrate. However, there was a catch. There were very few light sources to produce it. Enter the first stars. Born from this hydrogen and helium, these stellar pioneers emitted radiation strong enough to strip electrons away from their nuclei, reionizing the gas. This, combined with the universe's expansion, made the gas diffuse, unable to prevent light from shining out. And so, the universe's lights were switched on. The darkness of the cosmic dawn gave way to a fully illuminated universe, marking the end of reionization. This period, about 1 billion years after the Big Bang, was a turning point in the universe's history. Yet despite this incredible transformation, a question lingered. What were the main sources of this light? The universe was now fully illuminated, but the question remained, what were the main sources of this light? The pieces of this cosmic puzzle were scattered across time and space, and as we'll find out in the next scene, it took a cosmic lens, a galaxy cluster, and an international team of astrophysicists to finally put them together. Scientists initially thought powerful sources like black holes and large galaxies were responsible for clearing the murky hydrogen. But the James Webb Space Telescope revealed a different story. Picture the early universe, a dark expanse filled with a dense fog of ionized plasma. Amidst this cosmic soup, small, ultra-faint galaxies began to flare to life, piercing through the fog with their light. These were the dwarf galaxies, the underdogs of celestial bodies whose role in the universe's evolution was far more critical than previously thought. Data from the James Webb and Hubble space telescopes suggest that these dwarf galaxies were the true light-bringers of the early universe. Astrophysicist Irina Chemerinska of the Institut d'Astrophysique de Paris explains, these galaxies produce ionizing photons that transform neutral hydrogen into ionized plasma during cosmic reionization. It highlights the importance of understanding low-mass galaxies in shaping the universe's history. But how did these dwarf galaxies, so small and faint, manage to outshine their larger counterparts in the cosmic dawn? It turns out that these galaxies were not just abundant, but they were also much brighter than expected. Dwarf galaxies outnumber large galaxies by a staggering 100 to 1, and their collective output is 4 times the ionizing radiation usually assumed for larger galaxies. An international team led by astrophysicist Hakim Atek of the Institut d'Astrophysique de Paris relied on data from a galaxy cluster called Abell 2744. This cluster, so dense that it warps spacetime around it, formed a cosmic lens, magnifying distant light and allowing the researchers to see the dwarf galaxies near the cosmic dawn. Their detailed analysis revealed that these dwarf galaxies played a pivotal role in reionizing the universe. By emitting vast amounts of ionizing radiation, they transformed the neutral hydrogen fog into a clear, ionized plasma, allowing light to shine freely across the universe. It appears that these small but mighty dwarf galaxies were the ones that truly turned on the lights in our universe. So, the mystery of what illuminated our universe has been solved. We've journeyed through the cosmic dawn, witnessing the birth of the first stars from hydrogen and helium. We've seen how these early stars provided potent radiation, strong enough to ionize the neutral hydrogen gas and light up the universe. As the universe expanded, this ionized gas became diffuse, unable to obstruct the radiant light. The cosmic dawn gave way to the fully reionized universe, about 1 billion years after the Big Bang. Surprisingly, it wasn't the formidable black holes or the massive galaxies that played the lead role in this cosmic drama. Instead, the humble dwarf galaxies took center stage. These tiny galaxies, far more numerous and brighter than expected, were the ones that powered the reionization process. Their collective output was a staggering 4 times greater than the radiation emitted by larger galaxies. And there we have it, the lights of our universe powered by the unexpected heroes, the dwarf galaxies.